So for today, we will be discussing about gravitational potential energy and also power. So a short recap, we have the equations for work in terms of kinetic energy and also potential energy. So the work done or the total work done according to the work energy theorem is the change in kinetic energy. So again, this is from the work energy theorem. So last meeting we've discussed all about this one, and also we have the total work done is equal to the change in potential energy. So we have big letter K for the kinetic energy and big letter U for the potential energy. So this is our formulas to get the total work done in terms of kinetic energy and potential energy. So now, when we proceed to potential energy is the stored energy that depends upon the relative position of various parts of a system, and also it is the stored energy of position possessed by an object. So we have two types of potential energy. The first one is what we call the gravitational potential energy. So the symbol for this one is we have U grav for the gravitation, or we can also have it as U sub G. So that is how we would determine na this is a gravitational potential energy. So it's either U grav, U sub grav, or U sub G. While for the elastic potential energy, we have U sub L, EL, or we can also have it as U sub E. So it's either E for the elastic potential energy or EL. So nalang anang duha. Okay, so now we start with the gravitational potential energy. So gravitational potential energy is the energy stored in an object as a result of its vertical position or height. So gimension jud na vertical position, which is on the y-axis. So we have right here our equation for the gravitational potential energy. U grav, or again we can also have it as U sub G, is equal to M times G times Y, or we can also have it as mgh, or M times G times H. Okay, so now if we want to solve for the work done by gravitational potential energy, di ba, work is equal to force times distance or displacement. So our force is our weight. So considering here our figure 7.2, we have a box that is moving downward. So the force here is the weight. The force na nag-act sa imong object is our weight times the distance. So the distance is the difference of y sub 1 and y sub 2. So si y sub 1 is the distance, the vertical distance or position gikan sa iyang initial position up to the ground, while y sub 2 is the final position of your box from the from the final position of your box to the ground. So that's why we have y1 minus y2. So the work done by the gravitational potential energy on the box is we have mass times gravity. Kaya di ba weight is equal to mass times gravity man. So that's why we have mass times gravity times y sub 1 minus mass times gravity times y sub 2. So again, since di ba from the recap, we have the total work done is the change in the potential energy. So that's why the potential energy is equal to mgy, or mass times gravity, times the height sa imong body, or mg times y. So this is our equation for the gravitational potential energy. Okay, so balik ta sa work done by gravitational potential energy. Diba we have work done by gravitational potential energy is equal to, we have mass times gravity times y sub 1 minus mass times gravity times y sub 2. Now, si mass times gravity times y sub 1 is our initial gravitational potential energy, and m times g times y sub 2 is our final gravitational potential energy. Okay, so notice here sa next na line is si final gravitational potential energy is na siya dire first in line. So that's why we have this negative sign here. It's because si u grav or si final gravitational potential energy negative man siya. So by putting final gravitational potential energy first here sa atong equation, that's why we have this negative sign. Okay, if we multiply this negative and the gravitational potential energy nga final, so negative, same ra gyapon niya ang value, but nag-change lang ang position niya. So, we have here the work done by the gravitational potential energy is equal to the negative of the change in the gravitational potential energy. So, ang purpose nga nung ato ang gi-exchange ang posisyon ni initial and final nga gravitational potential energy para, di ba, when we say change is the final value minus initial value. So, that's why we have giuna nato si final value of the gravitational potential energy minus the initial gravitational potential energy para we can have the change in gravitational potential energy. So, si work done daw by the gravitational potential energy is just equal to negative of the change in gravitational potential energy, which is still this one. Okay. So, now, diba, we have two types of potential energy, the gravitational potential energy and also the elastic potential energy. So, elastic potential energy is the energy stored in elastic materials as a result of their stretching or compressing. Okay. So, when we say elastic, basic example of an elastic material is a spring. We also have rubber bands, or any material that is elastic. So, pwede na to na siya, or it has elastic potential energy. Okay. So, now, we have here, figure 7.13, A, B, C, and D. So, different scenarios ni siya for a spring that is either stretched or compressed, or as is. Okay. So, now, before we proceed, we have here Hooke's law. So, I will be introducing you Hooke's law. Hooke's law, mo ni siya ang formula sa force that is related on the spring. So, Hooke's law states that the force F is equal to K is our spring constant, times X. Now, kani si X, this is the position of your spring. So, pwede pod na we have, if na siya initial and final value si position, we can also have Hooke's law as F is equal to negative K times delta X. So, again, delta means a final value minus initial value. So, kung delta X, it is final position minus the initial position. Okay. So, unsa man yung negative? There is a formula sa Hooke's law. So, negative here, it's because ang force nga gi-exert ni spring, noticed here sa ato ang figure 7.13b, if you stretch the spring also exerts a force on the opposite direction or to the negative x-axis. Okay, so that's why we have this negative nga sign here for our Hooke's law. So again, this is our equation for Hooke's law. Is equal to F is equal to negative K times X. So, K is our spring constant, which is which depends if kung pila ang force nga imo ang gi-exert per meter or sa per distance na imo siyang gi-stretch or gi-compress. Okay. So, the work done on a spring, we have here work is equal to 1/2 times K times we have the final position squared minus 1/2 K times the initial position squared. Whereas the work done by a spring is we have work is equal to 1/2 K times the initial position quantity squared minus 1/2 K times the final position quantity squared. Okay. So now, diba, again, work done is equal to 1/2 K times delta x squared. Sa atong formula. This formula here, kani siya. This one. So we can also have it as 1/2 K times delta x quantity squared. Okay, so now take note na, diba, our work is equal to the change in potential energy U, which is equal to the final potential energy minus initial potential energy. So substituting the equation for work, which is 1/2 K times delta x squared here, in our equation, we have 1/2 K times delta x quantity squared is equal to final potential energy minus initial potential energy. Okay, so now again, take note na si delta x is, we have final or x sub 2, final position minus initial position quantity squared. So same ra gyapon sa right side sa equation. So distributing x sub 2 and x sub 1, we have 1/2 K times x sub 2 squared minus 1/2 K times x sub 1 squared is equal to, again, the same ra gyapon, final potential energy minus initial potential energy. Okay. Now, take note na si 1/2 K times x2 squared is for the final potential energy, and si 1/2 K times x sub 1 squared is for the initial potential energy. Okay, so that's why our formula for the elastic potential energy is, we have right here. So formula for the elastic potential energy is 1/2 K, which is the spring constant, times x squared. Or if you want to solve for the work done by the elastic potential energy, so work done by the elastic potential energy is just equal to the negative of the change in the elastic potential energy. Same with tong sa gravitational potential energy. Okay, so we have these two equations right here for the elastic potential energy. Okay, so now here we have an example that is related to the elastic potential energy. So we have a woman weighing 600 newtons steps on a bathroom scale that contains a stiff spring. So we have here in figure 6.21. So mo ni ang atong illustration. So in equilibrium, the spring is compressed 1 centimeter under her weight. So we need to find the force constant of the spring, which is Ck, or the spring constant, and also the total work done on it during the compression. So we need to find these two variables, which is, the first one is the spring constant, and the second one is the work done. Okay, so Now, to solve for the spring constant, di ba, ang ato ang given values are only the weight of the woman, which is 600 newtons, and also x, or our final position after ning step ang woman sa bathroom scale. So this is our x sub 2, which is negative 1 centimeter. Okay, ano man. Now, notice here in the figure nga na siya gibutang nga ang upward niyang direction is on the positive x. So, it means, since pag-step sa woman sa bathroom scale, na-compress siya for 1 centimeter. So, that's why we have negative. It's because ang direction sa compression is going on the negative x-axis. So, that's why we have negative 1 centimeter. Now, we still need to convert negative 1 centimeter into meters. So, negative 1 centimeter in terms of meters is equal to 0.010 meter. Okay. So, now, to solve for the force constant on the spring, or the spring constant, diba, from the Hooke's law, we have F is equal to negative K times X. So, to solve for K man nga itong ipangita, so we need to divide both sides with negative X. So, makancel out is the negative and X as well as this one. So, to solve for K, we have F divided by negative X. So, substituting their values, our force is the weight. So, this is our force, which is the weight of the woman. So, 600 newtons divided by 0.010 meter. Okay, so if you have calculators, you can also check this one if you have the same result. So 600 divided by 0.010 is equal to 6 times 10 to the power of positive 4. And then the unit is Newton per meter. So this is our value for the spring constant K. So nanatay value sa K. Now, the next thing that we will do is to solve for the work done during the compression. So we have, di ba, nanatay value sa x sub 2. We have the value for our K. Now, our value for the initial position is obviously 0. Kay mo man itong initial yet, or before pa ning step ang woman sa bathroom scale. So, to solve for the work done, it is equal to itong formula nato for since elastic potential energy man ta, we have 1/2 K times x2 squared minus 1/2 times K times x1 squared. Okay, so we have the values of K, x sub 2, and x sub 1, so we can solve for the work done. Okay, so substituting their corresponding values, we have 1/2 times K is 6 times 10 to the power of positive 4 newtons per meter times x sub 2 is negative 0.010 meters quantity squared minus, we have 1/2 times 6 times 10 to the power of positive 4 newtons per meter. And then we have x sub 1 is 0 squared. So obviously, this one right here, since 0 times 6 times 1/2 is equal to 0, so this one right here will become 0. So, what mabili na lang is, we have work is equal to 1/2 times 6 times 10 to the power of positive 4 newtons per meter times negative 0.010 meters quantity squared. So, mo na lang na siya yung mabilin. Okay. So, this one right here, meter quantity squared is meter squared. So, makancel out ang isa ka meter sa imong meter squared and the 1 over meter, makancel out na siya. So, di ba, this becomes meter squared. So, makancel out ang isa ka meter. So, the unit for work is Newton times meter, or we have joules. So, if you will calculate this one, 1/2 times 6 times 10 to the power of 4 times the square of negative 0.010, it is equal to 3.0 joules. So, you can also recheck this one if you have calculators. So, this is the work done by the elastic potential energy or by the spring. Okay, so that is for the example for the elastic potential energy. Okay, so now, what if we have both the gravitational potential energy and elastic potential energy in one situation? So, if we want to solve for the total work done, together with if we have both the gravitational potential energy and elastic potential energy, so we can solve for the total work done, which is equal to the work done by the sum of all the work nga present, which is the work done by the gravitational potential energy, plus the work done by the elastic potential energy and the other work done nga nag-exist pod sa imo ang body or sa imong object. So, since the total work done is according to the work energy theorem, since the total work done is equal to the change in kinetic energy, or it is equal to the final kinetic energy minus initial kinetic energy. So again, this is the work energy theorem. So we have the total work done is equal to, we have this one, the work done by the gravitational potential energy plus the work done by the elastic potential energy plus the work done by other forces is equal to final kinetic energy minus initial kinetic energy. Now, since the work done by gravitational potential energy is equal to the initial gravitational potential energy minus the final gravitational potential energy, and the work done by the elastic potential energy is equal to the initial elastic potential energy minus the final elastic potential energy, then if we will substitute this one, we have from the previous one, we have right here, we will obtain K sub 1 plus we have the initial gravitational potential energy plus we have the initial elastic potential energy plus the other work done, or the work done by other forces, is equal to, we have K sub 2 plus the final gravitational potential energy plus the final elastic potential energy. Or, we can also have it as K sub 1 plus U sub 1 plus the work done by other forces is equal to K sub 2 plus U sub 2. Okay, so wherein U is the sum of both the gravitational potential energy and elastic potential energy. So we have right here the work done by all forces other than the gravitational force or elastic force is equal to the change in the total mechanical energy E. So, by the way, mechanical energy E is equal to the sum of the kinetic energy and the potential energy of the system. So, this is our, if ever na we have situations that both deal with gravitational potential energy and elastic potential energy. So we can use this equation. Okay, so that involves the initial and final kinetic energy. K sub 1, we have K sub 2. We also have the initial and final potential energy. So potential energy is equal to the sum of the gravitational potential energy and elastic potential energy, and also the work done by the other forces. Okay, so here we have an example related with the combination of both gravitational potential energy and elastic potential energy. So example, we have here a glider with mass m, which is equal to 0.200 kilogram, sits on a frictionless horizontal air track connected to a spring with force constant K, which is equal to 5 newtons per meter. So we have the mass of the glider and also the spring constant K. So you pull on the glider, stretching the spring 0.100 meter and release it from rest. So the glider moves back towards its equilibrium position, which is ang iyang position at rest, x equals 0. So what is its x velocity when x is equal to 0.080 meter? Okay, so now here we have our sketches and energy bar graphs for this problem. So at point 1, we have the spring constant, which is 5 newtons per meter. And then you stretch, gipull nimo ang glider, gi-stretch nimo at 0.100 meters. So muna ito ang first na situation. And then so we have mo ni ang kaning broken line here, vertical broken line is diri ang ato ang equilibrium position sa imo ang spring. So x is equal to 0 and also our initial velocity is equal to 0. So after nimo gi-release ang glider, the glider moves back towards its equilibrium position. So this is our point 2 or our second situation. So the question here is, unsa ang iyang velocity when x sub 2 or x is equal to 0.080 meters. Okay, so here on the point 1, notice sa ato ang energy bar graphs, wala tay kinetic energy. Ang naalang energy is the elastic potential energy since you're stretching the spring. Whereas for point 2, kaning sa second na nato nga situation, we have now our kinetic energy and also the elastic potential energy. Okay, so now we need to solve first for diba, let's write our given first. We have the mass, which is equal to 0.200 kilograms. We also have our spring constant, which is 5 newtons per meter. And then we have our x sub 1, which is 0.100 meter, and our x sub 2, which is 0.080 meter. So those are our given values. So what we need to do is we need to solve first for k sub 1 we have U sub 1, U sub 2, and the last one is K sub 2. Okay? Anong pinaka-last man si K sub 2? Because, di ba, we have here K sub 2 is equal to 1/2 mass times V2x squared. So, that's why mo na siya atong pinakaulahin nga i-solve before ta makasolve ni V2x. So, this is our V2x right here. Okay. So, let's start with the initial kinetic energy K sub 1. So, K sub 1 is 1/2 m times V1x or V1 squared. Okay. So, we have 1/2 times the mass is 0.200 kilogram times our V1x is 0 according to, okay, since wala pa man siya nag-move, kay you release it from rest or gikan pa man at rest ang imo ang glider. So we have 0 squared. So obviously our initial kinetic energy is 0. So manata sa initial kinetic energy. Next is the initial potential energy U sub 1. So U sub 1 is equal to 1/2 times K times X sub 1 squared. Okay, so we have 1/2 times K is 5 newtons per meter times we have our X sub 1 is 0.100 meters quantity squared. Now, if we will calculate this one, it is equal to 0.0250, and then we have the unit for energy, both kinetic and potential, is in terms of joule or joules. Okay, and then the next one is the final potential energy, U sub 2, is equal to 1/2 times K times X sub 2 squared. So we have again 1/2 times K is 5 newtons per meter times we have X sub 2 is 0.080 meters squared, which is equal to 0.0160 joule. Okay, so you can just later on check if we have the same answers. Okay, so nanatay value sa K sub 1, U sub 1, and U sub 2. Okay, so diba from this equation right here, we have this one, kani siya. Money, we will be using this one, but instead we have no other work, so 0 ni si other work done. So we are left with K1 plus U sub 1 is equal to K2 plus U sub 2. So we will be using this equation. So we have K1 plus U sub 1 is equal to K2 plus U sub 2. So, since we are solving for K sub 2 or the final kinetic energy, we need to transpose the final potential energy to the left side of the equation. So, we have K sub 1 plus U sub 1 minus U sub 2 is equal to K sub 2. So, we have the value of K sub 1, U sub 1, and U sub 2, so we can solve for K sub 2. Okay, so substituting their values, K1 is 0 plus U sub 1 is 0.0250 joules minus we have our U sub 2 is 0.0160 joule is equal to K2. So our value for K2 is equal to 0.0090 joule. So this is our value for K sub 2. Okay. So now the last one is, again, we will be solving for V sub 2 using this equation right here. Okay. So now we have K2 is equal to 1/2 m times V2x squared. Okay, so solving for V sub 2, we need to divide both sides with m and multiply both sides with 2. Okay, so that we have 1/2 times 2 becomes 1. And we have m and m here will be cancelled out. So we have V2x squared is equal to 2 times K sub 2 divided by m. And then we will also get the square root on both sides para ma-cancel out si squared here and the square root sa itong V2x. So, V2x is equal to the square root of 2 times K2 divided by m. Okay, so substituting the values, natin values sa K2, we have the value for our mass, so we can solve for the final velocity if our position or when x is 0.080 meter. Okay, so we have 2 times our K2 is 0.0090 joule, divided by the mass, which is 0.200 kilogram. Okay, so our V2x is equal to 0.30 meters per second. Okay, so this is our V2x, or our, this one right here. So V2x is equal to 0.30 meters per second. So the velocity, this is the velocity when x is equal to 0.080 meter. Okay, so diba, when we get the square root, our answer must be plus minus in terms of plus minus. So by looking at the figure here, notice na si V2x is moving to the left side or going to the negative x-axis. So we will be choosing, so si V2x, our final answer for V2x is equal to negative 0.30 meters per second. Because again, by looking at the diagram or the figure, si V2x is moving to the negative x-axis. So that's why our V2x is equal to negative 0.30 meters per second. So that is it for our discussion for today regarding with the potential energy, which comprises of the gravitational potential energy and the elastic potential energy.